Okay, I want to welcome everyone out tonight to this May edition, May 2026 edition of our monthly Deep Talk series. It's great to see so many wonderful people out. My name is Mike Ray. I'm a science communicator here with SURF. My job is to be a mic stand tonight. I'll be carrying the mic for all of you to ask questions. For our wonderful guest tonight, Angela White, who's a PhD candidate working at the forefront of particle physics and the Deep Underground Neutrino Experiment, and the title of the talk is The Technology and Science Behind DUNE. So we're going to get to that talk in a little bit, but we always need to thank our sponsors, the folks who provide the wonderful beverages, wonderful food. Thank you to Crow Peak Brewing Company, who's been a longtime sponsor, Edward Jones Financial Advisor, Chris Mitchell, RCS Construction, and Charles and Jolene Lichtenwallner for their longtime support of this program and to helping bring conversations like this to lead South Dakota and to our community. We're also grateful for some special sponsors tonight. That includes Roundhouse Liquors here in Lead and Sawyer Brewing Company in Spearfish. They provided the wonderful beverages tonight. I also want to give a thanks to Rustic Nook as well for the great food. But at this time, I want to introduce Wendy Straub, the COO here at SURF, who's going to say a few words about those special sponsors this evening.
Thank you, Mike. Well, good evening, everybody, and I want to welcome you all to our Deep Talks this evening. Special welcome to those of you from the DUNE collaboration who have traveled a long way to come and check out our facility. We had a little bit of a schedule snafu this week with our regular sponsor, and so Tuesday afternoon I received a phone call, and I want to give a big shout out to Pam Millard with Roundhouse Liquors in Lead. She's located up here on the corner. Pam used to be an employee with SURF and retired a number of years ago and is a huge supporter of what we do here. So just wanted to give a shout out to her, who partnered with Sawyer Brewing Company and has provided our wonderful refreshments for this evening. So thank you and enjoy the talk.
Thank you so much, Wendy. And tonight, as I mentioned, we're really pleased to have Angela White, a PhD candidate working on the Deep Underground Neutrino Experiment, a PhD candidate at the University of Chicago. I think it's important to point out in the context of all of this, we often hear at Deep Talks events from researchers who've been involved in the career for their entire lifetime and who's standing on the shoulders of all the giants that make this kind of research possible. It's also really important to hear from early career researchers. And when you look at the history of physics, young people have had incredible contributions to physics and math. Wolfgang Pauli was only 30 years old when he came up with the idea of the neutrino. Albert Einstein was 26 when he started the theory of relativity. Ada Lovelace, if anybody's heard of her, she was 16 years old when she came up with the notion that you can use math to make machines do complex things. She was known as the first computer programmer way back in the 1840s. So it's really great to be able to hear from early career researchers like Angela White. And with that, I won't belabor the point anymore, but I'll turn it over to Angela. Thank you so much for being here tonight.
Oh. Okay, cool. Well, my name is Angela White, as you've already been told, and I'm here to talk to you a little bit about the science and technology behind the Deep Underground Neutrino Experiment, also known as DUNE, which is under construction here at SURF in South Dakota. I think maybe more than the usual general audience, you guys might already have a base knowledge of physics. So apologies if some of the slides are a bit simple. I promise we'll ramp up to the more exciting stuff eventually. All right. So if I start this talk with the question, how do we exist? You might think that you accidentally walked into a philosophy lecture, but I promise that isn't the case. This is a science question. How is it possible that the stuff that makes up you and me and the entire visible universe exists in the first place? It turns out that scientists don't actually know. All of the measurements that we've made to date pretty much point to the fact that nothing should exist. I can elaborate on that, but because you and I are here and the visible universe is here, we know we're missing something. So scientists understand that the universe is made up of certain building blocks. I'm about to use some words that might be unfamiliar, but don't worry, trust me, we'll circle back and we'll make sure everything's covered. So these building blocks are particles, and we call them quarks and we call them leptons. Quarks and leptons make up matter. So I'm made of matter. Everything we can see is made up of matter. All matter has these corresponding sort of inverse particles that we call antimatter. So a quark and a lepton have antiquarks and antileptons. Antimatter and matter basically behave the same, but sort of like mirror images of each other. So if a matter particle comes into contact with its corresponding antimatter particle, they cancel each other out and they produce a little bit of energy. And when I tell my friends about this, they're like, well, is that an explosion? And no, because particles are tiny. So if one particle comes into contact with another tiny antimatter particle, they'll produce a tiny amount of energy. It happens all the time, all around us, and we don't really notice. You could never notice because it's so infinitesimal. But we can actually measure this in physics experiments. So when antimatter and matter have been measured in science and the methods by which they're produced have been measured, what we've found is that matter and antimatter are produced in the same amounts nearly all the time at the same rates nearly all the time. So if you start with matter and then you produce the same amount of antimatter at the same rate, you should on average have nothing. And yet we're here. So we know that we have something. At some point, matter and antimatter had to have been produced at different rates or via different channels, and so they must sometimes behave differently. We actually do have some hint that this is the case. Quarks and antiquarks have been measured to behave slightly differently, but at such a tiny scale that it couldn't possibly explain you or me or galaxies, But now that we know that it's possible, we can start to look at that other set of building blocks called leptons. And specifically, we can start to look at this row on the bottom, these particles called neutrinos. We think that neutrinos and their antineutrinos could be responsible for the difference that we observe in the universe between the amount of matter that exists and the amount of antimatter that exists. Of course, neutrinos really don't want to be measured. So if we want to measure neutrinos and their antineutrinos and kind of figure all this out and understand how we're here at all, we need an enormous experiment. And that brings us to the Deep Underground Neutrino Experiment, or DUNE. So DUNE is a long baseline neutrino oscillation experiment. Again, if there are words that you don't recognize in that, we're going to get to them, so don't worry. DUNE is an enormous endeavor, not just physically, although it is enormous physically, but it's also enormous in terms of just collaborative effort. There are more than 1,500 scientists working on DUNE, which is a crazy number, even for large scientific collaborations. These scientists come from more than 37 countries. In fact, the 37 countries are just counting universities that are on DUNE, but universities can employ people from all over. So it's really a global effort. And if you look at this cavern that's here in Leeds, South Dakota, under us, I guess, you can see those little red dots. Those are trucks. So the scale is really kind of mind-blowing, and that's just going to hold less than half of our detector. So the Deep Underground Neutrino Experiment is actually being constructed in 2 different locations. The first location is at the Fermi National Accelerator Laboratory in Illinois. So this is where we're putting what we call the near detector complex. The near detector complex is where the beam is going to be produced that will create the neutrinos. And it's also where we put our first set of detectors, about 200 feet underground. And then the beam goes through the near detector, 800 miles through the crust of the Earth, and it travels here to South Dakota, where the far detectors are, a mile underground. So, what is a neutrino? I'm going to start quite simple, so bear with me. But neutrinos are weakly interacting neutral leptons with 3 mass states and 3 flavor states. That's the technical sentence. But we're going to build up the vocabulary. We're going to start at the beginning. So if you simplify things down, you can look at physics as basically the interactions between four fundamental forces. If you remember from high school, or if you just like reading, Newton's first law states that an object at rest is going to remain at rest, and an object in motion is going to remain in motion at a constant speed in a straight line unless acted on by an unbalanced force. So basically, forces are going to determine how things react and change in the universe. We've got our four fundamental forces. The first two you definitely interact with every day. If you've ever dropped something or looked at the moon, you've seen gravity in action, right? Gravity is active on the largest scales, and it impacts materials that are charged and not charged. The electromagnetic force, every time you plug something in, it's a force that acts on charged particles, so charged materials, and it basically gives you currents or magnetic fields. The strong force is really hard to describe. There's no good analogy, and there's not really any good examples. But basically, the strong force is what's holding the nucleus of an atom together. So it's important. But most important for this talk is the weak force, because the weak force is how neutrinos interact with other materials. The weak force is probably most commonly thought of as the force that sort of dictates nuclear decays, like you would get at a fission reactor. And the weak force is called the weak force because most of the time the other three forces are actually dominant. So because neutrinos interact with other particles through the weak force, most of the time they just don't interact at all. And that makes them pretty difficult to measure. So now that we've mentioned particles a bunch of times, we're going to walk through and sort of work up our vocabulary. So you might have heard of some of these particles, and we'll start with those. The proton is a positively charged particle. I want to tell you the mass, because the mass or the weight of particles is really important to us. But if I told you the number and the unit, it would be nonsense words. So I'm going to use an analogy with animal weights. This is not literal. But let's think of a proton as having the mass of 119 bison. All right. Another important particle is the neutron. The neutron isn't charged at all. It's neutral. And its mass is about 120 bison, so a little bit bigger than the proton. Protons and neutrons make up the nuclei of atoms, so that's relevant to the story. Another important particle is the electron. The electron is negatively charged. It's about one pronghorn antelope. We're keeping it local. So atoms have protons and neutrons in their nucleus, and then they have a cloud of electrons that sort of orbit around. All right, and most important for this talk is the neutrino. The neutrino is another neutral particle, no charge, and its mass is somewhere between half a sesame seed and nothing at all. So it is extremely small compared to all of the other particles. And that's, again, another thing that makes it so gosh darn difficult to measure. All right, so protons and neutrons can actually be broken down into quarks, which brings us back to our two sets of basic building blocks, right? And so that brings us to what we call the standard model. The standard model is basically a mathematical model that we use to describe all of the understanding of physics that we have currently. And it basically gives us these sets of particles, the quarks up here with 6 flavors, and then the leptons down here. Now, the neutrinos are these 3 at the bottom, and they come in 3 flavors: electron, muon, and tau. When I say flavor, you should sort of imagine like a subtype of a species. Like you could have a Chihuahua, a Rottweiler, and a Saint Bernard, and you would never, ever confuse them with each other, right? So just like that, an electron neutrino, a muon neutrino, and a tau neutrino, they have different characteristics that cause them to behave differently. So we can really pick them out when we're trying to detect them. So how do physicists generally learn about particles? Mostly we just take them and then we smash them into other particles, and then we measure whatever comes flying out. So we'll use another analogy. Think of the game of pool, right? You've got your cue, you hit the cue ball into the other pool balls, and the pool balls sort of scatter and go flying out. So in this case, the thing that you would be able to measure are the balls that go scattering away from the cue ball. Now, neutral particles are difficult to study because when particles scatter, we're able to measure them because they're charged particles. But if a neutral particle scatters, it doesn't produce a current, so we can't really see it. Think of, in this case, you hit your cue ball into a bunch of pool balls, but the one that scatters is invisible. So you know you hit something because your cue ball stopped, but you don't know if you scored. So there was actually an experiment that discovered the neutron, another neutral particle, and we can walk through how he sort of adjusted the pool analogy to figure things out. Basically, he took a nucleus and he launched it and smashed it into a big chunk of metal that was beryllium, and he was pretty sure that neutrons were coming out. But to prove it, he had to put a chunk of wax in front of where he thought the neutrons were. And the neutrons hit the wax and they knocked out a proton. Now a proton is charged, so he was able to measure that. And in doing so, he proved that something had hit the wax, so the neutron had to exist. Now, this is something that you can do in 1932 because the neutron is 120 bison, right? It's big. But how do you do it with something half a sesame seed? You know, it's a lot harder. The answer is basically you need an extremely high energy source of neutrinos to even attempt this. And now DUNE isn't the only way to do it, but we can look at that cue ball analogy and just sort of see the parallels with DUNE. We produce protons, we smash them into a piece of material, which is what we call the target. It produces that sort of invisible neutrino. And then we wait for the neutrino to hit the material in our detector and knock out more charged particles that we can actually see. So let's talk a little bit more about neutrino detection. It was first measured in 1956 outside of a nuclear reactor. So nuclear reactors produce really high energy neutrinos, so it's a good source to try to look for these. You have a lot of neutrinos and they're all very energetic. But it turns out there's also another nuclear source of high energy neutrinos near the Earth that we can use to try to discover things, and that would be the sun. So scientists in the 1960s were pretty sure that they understood how the sun was producing electron neutrinos, that one particular flavor. And so they wanted to try to measure them and, prove that they understood everything, which brings us to Leeds, South Dakota. So you've probably heard of the Homestake experiment, potentially. It was in this mine, and it was, deep underground, and it was specifically designed to measure that single flavor of neutrinos, the electron neutrino, coming from the sun. And it ran for about 20 years. It was basically a big tank of cleaning fluid. And by the end of its run, it had revolutionized our understanding of neutrinos as a particle, and it was well on its way to winning a Nobel Prize. So it's hard to understate how important Homestake was. This is actually the data plot from Homestake, and I'm going to try to explain it in a way that makes sense because it's a little confusing to look at just straight up. So again, Homestake ran for 20 years. And so when a scientist designs an experiment, other scientists make predictions of how many electron neutrinos are going to be produced by the sun, how many of those are going to travel through space to Earth, and then how many of those are going to go underground in Leeds, South Dakota and actually interact with the detector. So these orange dots are the predictions for how many neutrinos Homestake should have been detecting. And those lines that come out of the dots, those are basically just like a statement of confidence from the scientists. We call them error bars, right? Underneath those orange dots, you can see blue dots, also with error bars, and those are the actual measurements from Homestake. So over the course of 20 years, you can see that the error bars between the prediction and the data are actually overlapping a little, but generally the data is below. But after 20 years of running, Homestake took averages, right? And when you average over 20 years, you're able to shrink your error bars. So at the end of it, the prediction was 3 times higher than the actual measurement. And all of the neutrino physicists around the world were, scratching their heads and trying to figure it out. And everyone was trying to make sure that nobody had made a mistake. And by the end of it, everyone was very confident that Homestake had actually measured a real effect. So now we have to understand, what's that real effect mean? What's happening to all of the electron neutrinos coming from the sun? Well, first off, you have to trust the theorists who think they understand what's happening in the sun. And fortunately, they did know what they were talking about, and they were correct. So after that, the neutrinos are produced in the sun, and then they travel 8.5 minutes to Earth, which is a really long time, considering they're moving at the speed of light, right? So sometime in that 8.5 minutes, something happened. Now, it's important to remember that Homestake could only could only detect one of the 3 flavors, those electron neutrinos. So it was theorized that if the neutrinos oscillated between flavors, so if those electron neutrinos could become muon neutrinos or tau neutrinos as they traveled, then Homestake wouldn't be able to measure them. Nothing was disappearing. They were just passing through the detector unnoticed. So it turns out that was what was happening. And these oscillations are what eventually got Ray Davis the Nobel Prize. Now, DUNE wants to measure neutrinos, but we don't just want to measure neutrinos. We're pretty confident they exist. We feel good about that. We specifically want to study neutrino oscillations because we think that those oscillations can answer the big questions like why we're here and all of that, you know? So we produce our neutrino beam and we measure the beginning of it before anything's oscillated with our near detector, and then we let the neutrinos travel until they reach the far detector. And now they've changed, and we measure them again. And that's how we learn about the neutrino oscillations. But let's dig a little bit more into neutrino oscillations. What are they? This is called the PM&S matrix, and I just wanted to show it to you for fun. It's a mathematical object that physicists use to try to describe neutrino oscillations. Well, not try, we do. And it's difficult to look at. We're not going to try to understand it. But if any of you are in high school math or undergraduate math, you might recognize this rotation matrix. So it's fun to see that, you know, even complicated mathematics is building from the basics. Okay, but the one thing that is difficult that we do sort of have to understand to get into neutrino oscillations is quantum probability. You might have heard of the phrase Schrodinger's cat. Schrodinger's cat is a thought experiment, not a real experiment. It's important to note. Where you start with a cat. You put a cat in a box, and then with the cat, you put this radioactive thing that has a 50% chance of killing the cat if you give it an hour. So you put the cat and the radioactive thing in the box, and you close the box, and then you wait an hour. And during that hour, while you're waiting, there's a 50% chance that the cat's dead, and there's a 50% chance that the cat's alive. But Schrodinger's point was that while that box is closed, before you measure the cat sort of exists in 2 states. It's 50% dead and 50% alive. It's both states simultaneously. So that's kind of what quantum probability is for a particle. A particle can exist as a probability split between different states. And until you open the box and measure how dead or alive your cat is, it doesn't, it's not either one. It's all of them simultaneously. So we've got another analogy to try to dig into that a little bit more. So we have our 3 neutrino states, the flavor states. And we're going to ignore the last one, because when you add a third, it gets really complicated. So we've got our 3 neutrino flavor states, and we're going to imagine that we have 2 clocks. The purple clock is a normal functioning clock. The minute hand moves around 1 time in an hour, and that's great. The green clock is messed up. I'm not sure why. The minute hand moves around in 42 minutes. That's just a random number. It's not important, so you don't have to remember it. So when the purple clock is pointing to 1 and the green clock is pointing to 4, that's when we're going to say we have a 100% chance of measuring an electron neutrino. And when the purple clock is pointing to 9 and the green clock is pointing to 11, that's when we're going to say we have a 100% chance of measuring a muon neutrino. So if we start out with a muon neutrino and those 2 clocks in that particular configuration, and then we start them and we let them run, as soon as those hands move off of those numbers, we don't have a 100% chance of measuring a muon neutrino anymore. The cat's in the box. Now we've got a probability. We've got some probability of measuring a muon neutrino and some probability of measuring an electron neutrino. But we're not going to measure it yet. We're going to let that neutrino keep traveling, and we're going to let the clocks continue to run. Eventually, and not in an hour, because our clocks are moving at 2 different speeds, your hands will wind up with the purple clock at the 1 and the green clock at the 4, and then you know that you have a 100% chance of measuring an electron neutrino. But again, we're not going to stop our neutrino. We're going to let it keep traveling. Boom. Now we've got another mixed probability state. But if you let it go long enough, these are periods. It oscillates. So eventually we get back to the point where you have another 100% chance of measuring a muon neutrino. And this is kind of the idea underpinning neutrino oscillation experiments. Now, just to be thorough, what we actually call this is a superposition of mass states. And in this analogy, the purple clock is the first mass state, and the green clock is the second mass state. And there's actually 3 mass states that you have to use to completely describe neutrinos. But the point I want you to take away from this is that if you're designing a neutrino experiment and you know you're starting with this flavor and you want to measure the oscillation at its highest point, then you actually have a handle because you can choose where you put your detector. And the distance that the neutrino travels is going to determine how much it oscillates. So if you're building the DUNE experiment and you want to study neutrino and antineutrino oscillations, you place your detector at a point where you know you can start with one flavor, and by the time it gets to the far detector, it's not likely to still be in that state. And that's pretty much what DUNE has done. And that's why we have to be 800 miles away from the beam. So how does DUNE actually measure neutrinos? So to detect neutrinos, you need, first off, a whole lot of neutrinos. And they have to be at a very high energy because, again, and not to belabor the point, neutrinos really don't want to interact with anything. They're weakly interacting. We also need a whole lot of very dense detector material. I mean, we've seen a couple of pictures of the cavern already, but I can't impress enough on you how enormous it is. And we're going to fill that with target material. You also need a readout with a very high resolution. So basically what that means is these particles are very small, so the signals are very subtle, and you need to make sure that you can pick them up in your detector. And the last thing we need is a very low background. Background's basically false signal. So we'll start with the beam. The PIP2 neutrino beam is being constructed at Fermilab as we speak. By the time it's completed, it will be the most intense neutrino beam in the world. PIP2 is going to create trillions of neutrinos every second, and it's going to blast them through the Earth towards South Dakota. But again, because neutrinos are weakly interacting, most of those will never do a thing. They'll just go straight through. Now, this little white building here is actually a 16-story office building, just to give you an idea of the scale. The PIP2 beam starts producing protons here, and they're sort of looped around here and fed into this big loop that we call the main injector. And in the main injector, the protons are cycled around until they reach an energy that's high enough for what we want to do. And then, just like that pool experiment, we launch them straight into the target here. And at this target, a whole bunch of things blast out, they decay to neutrinos, and we get our neutrino beam heading to South Dakota. That's the neutrino beam. The second thing we need is the detector material. Lots of it and pretty dense. Liquid argon is a dense material. It's denser than water, but it has some other characteristics that make it ideal for a neutrino experiment. First off, when particles interact with an argon nuclei or an argon atom, the argon atom produces both electrons and light. So that's great because anytime you can get 2 signals for the price of 1, you're really helping yourself out. The other thing that happens is argon is a noble gas. That means it's inert. It doesn't really want to take in electrons. A lot of elements do, so it's great to have argon, especially because, as I said in that first point, one of our main things that we have to measure are these electrons drifting away from the interaction points. So if the argon were to try to absorb those electrons, we would lose our signal. We wouldn't get it as crisply and clearly as we need to. So argon being inert or a noble liquid is extremely important. If any of you are, up to date with the Lux or LZ experiments here at the lab, those are also noble liquid experiments for similar reasons. So again, it's difficult to impress on you how large these things are. Another local example is that if you have a 17 kiloton detector full of liquid argon, you can fill one corn palace. I'm talking second floor, I'm talking bottom floor, I'm talking hallway and bathrooms. The only thing I am not counting is that big bulb on top. And that's just one of the FAR detectors. We're going to have 2 to start with. So we're also going to have this second complex, the near detector complex that I already talked about. And it's important for the oscillation measurements because we need to know what flavor the beam starts with and we need to know what energy the beam starts with before it blasts off. I think it's important to note that of the trillions of neutrinos produced by the beam every second, only about 60 are going to interact in the near detector every second. Now that is a massive drop. And I think now you sort of understand what weakly interacting means. But actually, 60 neutrino interactions in one detector is way more than we are used to dealing with. It's kind of intimidating. So we've had to make a whole bunch of sort of developments to the liquid argon technology at the near detector to make sure that we can handle that. And I should mention, the near detector complex isn't just a liquid argon detector target. We have some other ones to sort of help us characterize that beam. But for this talk, we're just focusing on the liquid argon for the sake of simplicity. Also important to note, those 60 neutrinos that are interacting, those are pretty much just for detector and beam characterization. The neutrinos haven't oscillated yet, so the interesting information that we want to learn isn't really encoded in the neutrinos' behavior. So what we really care about, or I suppose not what we really care about, but what we really, really need to measure, are the neutrinos that interact at the FAR detector here in LEAD. And again, trillions of neutrinos produced by the beam every second. Of those, less than 100 will interact in the FAR detector every week. Every week. Now, if you've ever taken a flashlight and you've shown it at somebody who was maybe a foot away, straight in their eyes, it probably hurt them a lot. That's sort of what's happening with the beam at the near detector. But if that person walked half a mile away and then they turned around and they looked at your flashlight, they'd be perfectly fine. It's dim, the light's a cone, it spreads out. The neutrino beam is like that. It's not a laser, it's more of a flashlight. And so by the time it hits that FAR detector, it's probably about a mile wide. And we can't build a mile of liquid argon detector. So that's sort of why the rate's quite low. But because the rate is so low, a lot of thought and a lot of time has been put into the design of the FAR detectors to make sure that we can capture every single one of those interactions that happen there and eke out all of the oscillation physics that's encoded in those neutrino interactions. Now, how do we actually measure the neutrino interactions? What's the technology? It's called liquid argon time projection chambers. The time projection chamber pretty much just means that we take the current from these interactions and we reconstruct them into 3-dimensional images. And we, sort of understand what's happened in the detector using that. I'll give you some real-world examples later, but first let's walk through the actual structure of the detector. Imagine a cube of liquid argon. Now, on one side, you put a cathode, which is basically a metal sheet that's negatively charged. Opposite the cathode, you put another metal sheet. That's called the anode, and that's positively charged. Or it's positively charged relative to the cathode. And because you've got that differential, you create an electric field across the volume of your detector. And for liquid argon experiments, it's really important to us that we keep that field as constant and as uniform across the whole detector as we possibly can. Now, when a particle comes in, it interacts with the argon nuclei, this particular example particle is interacting with a heck of a lot of argon nuclei, so it's not a neutrino. Maybe it's a proton, right? The interaction occurs, and the argon atoms produce those electrons that we talked about. And because we've put electrons in an electric field, the anode is relatively positively charged and opposites attract, the electrons are going to start drifting across the detector volume. Again, because argon is inert and it doesn't want to interact with those free electrons, that means that the electrons drift in exactly the formation that the particle track created. And so we get kind of a preserved image as it moves towards the anode. At the anode, those electrons become current and we can measure them. Now, we need some real-world examples because that's, I don't know, abstract, it's a cartoon. And fortunately, DUNE is such a massive experiment that we've had to do a lot of prototyping. And there are some pretty incredible prototypes that have been operated around the world. First one I want to talk about is called ProtoDUNE. ProtoDUNE is actually 3 prototypes, and they've all been built and operated at CERN, which is a big physics lab in Switzerland. I don't know exactly which prototype this picture is of, but it should give you an idea of the scale. The ProtoDUNEs are prototypes for the far detectors, the ones that will go here. So they're massive, right? This is a man. He's on a relatively tall lift. He's only halfway up. So sizable. Now, these pictures here are actually event displays. So this is the data read out from the detector. These are the electrons that we've drifted. This particle up here is a straight track. It's not doing very much. It's pretty clear. It's pretty crisp. We know that this is a proton. We can tell just by looking at it. And down here, this like hairy-looking track that's doing some weird stuff, that's an electron. It's a high-energy electron going through the detector. So when we look at these tracks and these event displays out of the detector, we're able to tell which particles are which. We're able to tell how much energy they dumped in the detector when they came and they interacted. So we're able to use that, sort of like, you know, a crime scene, to reconstruct what happened when a particle came in. These are a couple more pictures of ProtoDUNE because I think it's really cool. This one's called the vertical drift. So up here we have the cathode. And down here, it hasn't been installed yet in this picture, but they would put the anode. So again, this is basically a tall room. And the argon is inert enough and clean enough that we can actually drift electrons, tiny electrons, in a strict, tight formation all the way from this cathode down to this anode, which is remarkable. This is called the horizontal drift. We're actually just sort of looking at the side. We're not even looking in it. And this part right here is the anode, which for this particular prototype is a bunch of interwoven sort of very, very tiny wires that are able to give you very, very precise measurements of the electrons coming from the rest of the detector. Now, there's another prototype that's actually happening in the US at Fermilab, and it's called the 2x2 Demonstrator. This is what I'm doing my thesis on, so it's near and dear to my heart. I've spent the last 5 years with it. So you'll notice that this one looks pretty different from the ProtoDUNE detectors. For one thing, it's quite small. Tom Murphy's over there. You can see he's not a giant. In addition, you might notice that it's actually split up into 4 very sort of small sub-detectors. We do this because the near detector, which this is a prototype for, is going to get those 60 neutrino interactions. And if we didn't try to separate them from one another, the signals could actually get really confusing. So this is pretty new. It hasn't been done much in the liquid argon community before, and so far it's working pretty well. Now, here's an event display from the 2x2 demonstrator. This is also what the top of it looks like. Very tidy, right? Now, this event display is particularly exciting because so far you haven't seen what neutrinos look like when they interact in one of these liquid argon detectors. So the 2x2 demonstrator was actually operated in a neutrino beam, about the energy type that you're going to get at DUNE, maybe a little higher energy. And so when a neutrino comes into a liquid argon detector, it's not charged, so it won't create a track that way, and it doesn't want to interact with anything. In fact, if it interacts with anything at all, It'll probably just interact once. So when we see an event display where it looks like nothing comes in, and then suddenly there's a big cone of particles busting out, we know that that's a neutrino. So here we have two different neutrino interactions happening in this detector. In the 3D image, it's a little harder to see. But basically this and this right here, and you can see nothing comes in, everything bursts out. And then it's the physicist's job to look at those individual tracks and go, oh, I think this is a proton, I think this is an electron, I think I know what happened at the argon nuclei. So there's one more thing that we haven't talked about now that we're done with the detectors, and that's why DUNE has to be so gosh darn far underground. So when you're measuring very subtle signals, you want to make sure that you don't have a background or that your background is very low. Now what a background is basically imagine you're at a concert and you're trying to talk to a friend. It's difficult, right? And then compare that to trying to talk to your friend in an empty room. So much better. Backgrounds are basically noise. They threaten to drown out your signal so that you can't measure anything at all. And one of the most common backgrounds in particle physics is something called cosmic muons. So extragalactic and galactic objects like black holes or whatever, they sort of accelerate particles and they blast them towards the Earth. And those high energy particles hit nuclei inside of, or not inside, but they hit nuclei of particles in our atmosphere, and they produce this enormous shower. This might look like an exaggerated cartoon, but honestly, it's like kind of close to truth. These showers from this one little proton spread out over the atmosphere, and they have a lot of high energy particles sort of bombing down towards the ground. So if you're just on the surface of the Earth, you can get like 300 of these charged particles blasting through about 1 meter squared every second. And when you have a very delicate, sensitive detector, you're going to see all of that, and it's going to drown out your actual signal. So what you have to do is you have to start digging. As you go down a mile underground, eventually you're basically getting a negligible number of these cosmic rays. You might get a couple very, very high energy ones, but at that point they're pretty obvious, and you can just pick them up and throw them out. Now it turns out for a neutrino oscillation experiment, you don't actually need your cosmic muon background to be this low, but the fact that at DUNE it is going to be this low gives us the opportunity to do a lot of other exciting physics. I mean, the whole why do we exist question was already pretty exciting, but we can do more at the same time. One of these studies that everyone's pretty excited about is supernovas. When a star explodes, it actually blasts out this envelope of pretty high energy neutrinos, but by the time they reach the Earth, they're not necessarily easy to measure. And these neutrinos haven't interacted with anything in space because they don't like to. So they're basically perfect, pure little packets of information telling us what happened in the middle of a star right before it went, right? So that's great. We all like interstellar explosions. So this hasn't actually happened in a scenario where we were able to measure it since 1987. In 1987, there was a supernova somewhat close by, and we were able to measure 17 neutrinos. If 17 neutrinos seems small, it is. We can do much better today, and we can especially do much, much better with DUNE once it's turned on. So we're all really hoping that a supernova happens while DUNE is running. Unfortunately, DUNE's going to run for quite some time. This brings me to the end of the talk. But in conclusion, the DUNE caverns have actually been excavated. Everything's going really well, and the installation begins this year. DUNE's on schedule to take data in 2030, so we're really looking forward to sharing the results with all of you, and we appreciate you hosting us. Sure.
That was really great, Angela. Thank you so much. Audience, what questions do you have for Angela? We have some time. What questions might be out there about this wonderful research? Got one right here? We'll go up on mic 2, Stephen.
So with the 800-mile distance, what's the probability expected from an electron neutrino and going to a tau or a mu neutrino?
Well, we actually don't start with electron neutrinos at DUNE. Unlike Homestake, we're able to measure all three types of neutrinos, electron, tau, and muon. So let me get to the picture. Yeah. I don't know how well you can see this, but I actually got the probabilities into this little diagram. The green is the muon neutrino, and we start with mostly muon neutrinos. There will be some electron neutrinos in the mix. And as we head across the 800 miles, by the time it reaches the far detector, actually the majority of our neutrinos are going to be most likely to be measured as taus. But there will be some muon neutrinos there and some electron neutrinos as well. So we're not quite going from, well, I guess in my clock example, we only used true neutrino flavors, right? Because it's a lot harder to get, well, you don't really get like a, oh, at this point, you're 100% likely to measure a certain flavor once you've got three, because the oscillations are so complicated. But definitely at the far detector, our neutrinos have gone from most probably muon neutrinos to most probably taus.
Can I follow up?
Yeah.
Yeah, okay. So when you're measuring with a near detector, you're measuring a number of neutrinos, whether they're tau, and so then at the end of that 800 mile, you're comparing that with what started out. But how do you know which flavor the neutrinos change to in that distance?
Yeah, okay. Well, they actually produce, oh gosh, I have so many slides. Could I get to the good one in time? Basically, when a neutrino interacts, different particles come out of that interaction. Here we go. Okay, so I didn't really talk about these three leptons up here. I mean, I talked about electrons a little. But there's also a muon, which is basically a heavy electron, and a tau, which is like an even heavier electron. So when an electron neutrino interacts in liquid argon, what comes busting out is usually a forward momentum electron. You might remember that from one of the event displays, the electrons are quite hairy. We call them showers. So they're very distinctive. When a muon neutrino interacts, a muon, a forward-going muon, comes out of that cone. And muons, when they're high energy, don't really stop for anything. So at the near detector, we're basically going to say a particle is a muon neutrino interaction if it's got this long line coming out of it that busts through all of our detector materials and doesn't stop. And at the DUNE detectors, the far detectors here, they might be large enough that the muon might actually stop. But when a muon stops, it decays to something we call a Michel electron. So again, there's actually a little visual cue that says, oh, that was a muon neutrino interaction. For a tau, the tau neutrino interactions will produce a tau, and a tau is crazy heavy, and it actually just creates this chaotic nonsense of track, and it just like, it's like an explosion in your detector. It's not really, because it's such a low energy thing, it's just one particle. But in the detector, it looks crazy. So that's how we know a tau has happened. And the far detector might actually be large enough that we can really study those tau neutrinos. But if you get a tau neutrino interaction in the near detector, there's not a chance you're going to contain that thing. No.
Wow, that's great questions. What other questions might be out there? We got one right here.
So with the near detector where it goes out like a flashlight versus like a laser, is there a way to like make the neutrino turn into like a laser to go through there? Is there a benefit to like having it kind of cone out like that?
So the problem is that when we smash the protons into the target, what comes out are charged particles with a very short lifetime. Basically, they lose the will to live and they decay into neutrinos. But we use those charged particles with a short lifetime, and we create a magnetic field to like point them towards the DUNE far detector. And we point them as well as we possibly can, But ultimately, to get the neutrino, we need them to decay, and we can't control the direction of the neutrino when it decays. So that kind of creates the spread. Because neutrinos aren't charged, we can't use magnetic fields to point them better. Yeah.
Another great question. What other questions might be out there? Audience, what other things you want to know about the Deep Underground Neutrino Experiment or some of this science? Got one back here. Anne's got it.
Can you elaborate a little bit on the existential question that why do we exist?
Sure, yeah.
Nice.
That's an easy one. Yeah.
So the question of why do we exist from the scientific angle is basically why is there more matter than antimatter? And so if we study both antineutrinos and neutrinos in DUNE, and we study their oscillations, and we get different, well, I don't want to use the right words because they'll be nonsense words. We have a pretty good idea that they behave quite differently. And if they behave differently enough, it's called a mixing angle. If this value that we can measure with DUNE is large enough, then that means that when neutrinos were sort of washing around in the early universe, the difference in behavior between the antineutrinos and the neutrinos would be enough that it would cause these sort of fluctuations of matter that could survive and grow into what we see in the present day. So really, we're just trying to measure that value, and we're hoping it's large enough.
Great. What other questions might we have? We have a little more time. What others might be out there? Got another one right back here.
I think you answered this with the first question, but why 800 miles? Is it so you can detect that other neutrino that you haven't been detected before?
Well, I mean, it's cool to get a massive sample of tau neutrinos. That'll be pretty neat. Nobody's really got more than, I don't know, tens in their detector before, and we're going to get so many. So that is cool. But part of it is that we needed to hit a point in the oscillation where enough had happened that we could get a clean measurement. And it also really helped that your mine was right here. That was great.
That's a stroke of luck for
Yeah.
for surf. It was a very good deal.
Yeah.
We have one right here, please.
And I apologize, I left for 10 seconds. How are you, I guess I don't know if I missed it, but how are you proving the oscillation? Like, how are you proving a change?
Oh, sure. So basically, if you measure at the near detector the initial makeup of the beam, you know that you've got, some amount of electron neutrinos when you measure there, and you know you've got some amount of muon neutrinos when you measure there, and we'll forget about the taus for now, right? You can say, okay, if particles can't be destroyed, and I know that I've got this mixture of neutrinos here, and I'm about to launch the beam x distance, you can do the calculation and you can predict how many of each flavor you should measure at the far detector. You have to make allowances because you're getting a higher percentage of that flashlight beam through your near detector just because it's closer and because we can't make the far detector large enough to match it perfectly. But those are just little mathematical tweaks that you can do. And so you have a pretty good expectation, and then you measure the expectation and you look for deviations and that sort of thing.
Okay.
Yeah.
Great questions. What others might be out there? Might we have? Anybody have any burning questions? I got one back here.
Thank you for a great talk. I mean, having seen a number of presentations about DUNE, I think really the most approachable presentation we've ever heard. So thank you so much. And so for those in the audience, if you wonder what you just heard has value, my wife texted me while you were giving your presentation, and she said muon neutrino was the answer for a Jeopardy daily double question today, and she answered it correctly. The contestant did not and lost $4,000.
That's excellent. That's excellent. What else might be out there? What other questions might we have? We're coming near the end. We have time for a few more. Please, you've got one here, and I'll get one more.
Curious, are neutrinos directional?
Are neutrinos directional?
Directional. Does the rotation of the Earth, will it affect the ability for the catcher to
I get what
do
you're
its
saying.
job?
So the neutrinos are traveling at the speed of light, given the medium it's in. So it is traveling through the Earth. That changes things a little. But basically, the neutrinos from the beam are produced in a tiny fraction of a second. And they'll reach South Dakota in a fraction of a second. So they're not traveling through the Earth long enough for the rotation of the Earth to really have a big impact.
A little faster than 990 maybe. we have another one here.
Sorry, can you explain really quick what antimatter is? Like, how do we know that that exists if we can't see it? If we can't, like how do we know that's there?
I mean, okay, so you can't see it in your day-to-day life, you know, like I can't see an electron right now either. But in these particle detectors, a positron looks like something, you know, we can see it. It interacts with other matter pretty much the same way an electron would, and things just get weird when it meets an electron, you know? So we've definitely seen tracks from antimatter in these detectors, and we see them all the time. Actually, my thesis measurement is really complicated by the fact that I can't tell the difference between a muon and an anti-muon. They look exactly the same.
Got time for maybe one more question. What other questions might be out there? Anybody have one more? Yeah, please. That's wonderful. No, please, yeah.
Like at the end of it, you say the existence of everything, you know, this will help explain all of that. What is the end, you know, idea there of knowing, you know, how everything is and why?
I think it's the particular characteristic of a scientist maybe, is that if you don't know why, it could keep you up at night.
Well, let's give Angela one more round of applause. Absolutely fantastic talk. Just a couple of things I want to note. Tomorrow, Friday, from 4 to 5 p.m. over at the Homestake Opera House, everyone's welcome to come for a cultural presentation featuring Star Chief Eagle and the Hoop Dance. So that's open to the whole community. Please come over at 4 to see that. And our next Deep Talks is on June 23rd. It's going to be with Dr. Caleb Joukowsky on the challenges of carving Crazy Horse. So we hope to see you all back out on June 23rd. Thank you so much for coming out tonight. If you have more burning neutrino questions, I think that Angela might stick around a little bit